Okay, perfect. So, may I start? May I? Okay, thank you. So, hi everyone, I'm Lorenzo Racchetti, and my tutor and co-tutor are Luigi Biagiotti and Cesare Fantuzzi. And I'm here to summarize you my years of PhD activities about improving the software development for automation, in automation, sorry. So why does this work? Because basically there is actually, in the last few years, the software the cost of the software in automation has doubled. And this is mainly due to the fact that there is an increasing complexity in software automation, which created a few new challenges, like from the usability to the lifecycle management of the software and machineries. And to the best of our knowledge, there is not any work that meets all those challenges altogether. So, to give an idea how important those challenges are for the domain, we propose you an example. This is a filling machine of one of our industrial partners, and it happened that the motion component of this filling machine just became obsolete, so it was not sold anymore. And this filling machine was on the market just from 5 years, so it was a big mess. And so our partner had to find a new motion part from the device to the software, and also do new tests, new verification and validation, and also do that in really tight timings, as there are clients that wanted their filling machine, and so there were time constraints that had to be satisfied. So this experience basically threw some question, like is it possible to improve the code flexibility in a way that you don't have to change all the code when something changes in the hardware? Or simply, how then I can increase the maintainability of this software? And finally, how can I handle in a better way the life cycle, like keeping track of each version of the software and also of the different customization for the clients? So, if you notice, basically we would want something that there is an analogy in computer science on the PC. So for example, now I am using this PC, and I can use the trackpad on this application, on the presentation, but if I change with that mouse, the application doesn't bother about the change of the hardware. So we would like something like that. Like the applications still go on, also if we change the hardware, of course with an hardware that is compliant to the specification of the machine. So basically we look at the start also to the state of the art, both in automation, like Faldella's work were really interesting, to also the computer science one. For example, the Gang of Four, which is really famous in computer science. They were the guys that made the design patterns and so on. And so, as also Vogel and Mr. Vyatkin said in their work, however, the list of open issues in this domain about these new challenges is still open and long. So, what's our aim? Basically, we want to meet those current challenges during all the whole process of software development in automation, from the requirements to the maintenance of the software. And so we started looking at which was the situation, and we noticed that basically in all our industrial partner there was a set of actuators and sensor connected to a PLC. And then on this PLC there was a software application which was in charge of handling those devices and the control logic of those devices, and also the process of the machine. So basically there is an hardware platform in automation and a software application. And from our experience, we learned that usually the software application is tailored just for the automation hardware platform, which means that in the software there is a part that handles the hardware, which is brought all together with the control logic, which means that if you change something in the hardware, you have also to redo and rewrite all the control logic, which is not the most flexible way for doing the software in control. So we proposed to reorganize the previous architecture in a 3-layer one. There is still the hardware platform, but just above there is the software for that we call abstraction. Actually is all the software that is in charge of handling all the devices, all the hardware. And it also has to provide a standard and public interface to the real software application, the one that is in charge of controlling such devices in order to produce the deliverables of the machine. However, there are actions in automation, like for example for an axis handler, that require several PLC cycles. For example, for an axis, if you do a positioning or a jogging or a homing, it takes more than a PLC cycle. So we had to handle such action through all those PLC cycles until the action would be ended, done, aborted, or it gave through an error. And for computer science, it's really easy to do that because there are tools like the threads. So we say, okay, this is the action, this is the function that handles that action, and we can link it to the thread. And then the thread starts to live its own life, and it survives through the cycles until the action is done. But in automation, there is not any tool like that. So we had to overcome this issue, and we decided to deal such action by modeling this reactive behavior of such action of such devices and also of the control logic by using state machines, which means that actually there will be state machines that handles the control and handles the process, which commands state machines of the device that they use. And those devices then will also use other state machine that will represent the action of such devices. So, for example, if the control logic want to command, want to do a certain action on the system, then it has to command the state machine of that specific device or of the set of those specific devices. And those devices then will handle the action by communicating with their own state machine of the actions. But there is an issue. Actually, there are several kinds of devices. Like, for example, there is not an axis handler. There is a generic axis handler, and there is, for example, an axis handler which use CAN bus or EtherCAT or Ethernet IP, and then there are axes that are produced by some brand, for example, Beckhoff, Rockwell, or whatever, and all of those brands have several versions and several devices that has differences. So to handle those differences, we use basically object-oriented, which means that we start with a component, a software component, which represents a generic device in automation, and then we extend it, adding new features and more specific details about this component by making components for all the specific families of devices. And then we can continue by extending such components by providing additional information about that specific version of that hardware. For example, AX5000 of Beckhoff or XTS of Beckhoff or whatever by Rockwell, Siemens, and so on. So this is a good approach because we are using object orientation features to introduce the specification of the software components, and it increases also maintainability and reusability. However, it also increases the complexity of the software because it becomes more difficult to understand who does what. Okay, and so to handle such complexity that we introduced, we also created an automatic documentation generator, which we called DATE, which stands for Doxygen for Twinkle 3. And basically, it is a tool that parses all the code from your PLC or PLCs, basically your projects, and it goes to parse all the code, both the commented one by the developers and the uncommented one. And then it provides you the updated version of the documentation for your specific version of the software, which allowed us to increase the usability, to reduce the complexity, because it is easier to have, to generate a specific documentation of that version of the software. For example, I want to know which are differences among those two versions of the software. Then I can generate the documentation and read and understand which are the differences. So improving also the lifecycle management. So an example of we obtained, basically these are two examples of code. This is a function block, and this is another function block which extends that one. And here we have the part of the documentation that we obtained. So now that we dealt with the flexibility, the maintainability, the usability, and so on, we also had some issue on the testing. In fact, we say that we were using a state machine to manage the multi-cycles action. And it happened that during our developing, we changed the implementation of such state machines. And we increased the performance, but the previous tests that we have done were referring to the performance of the previous version. And so we had to redo all the tests of those state machines. And then we thought about, okay, but we made something wrong. The tests had not to depend by the implementation of the code. And so we started to find a new way for building testing that were not dependent by the implementation. And so we saw that actually we had all the information for generating those tests in the specification of our software. And so we decided to use the timing diagrams inside our specification, which are diagrams that provides information about the dependencies among the signals and also the time constraints among those dependencies, to generate the test, to download on the PLC, to run the test, to obtain the result, and then to compare the specification wanted results to the actual results, and then provide the reports about this comparison. So, is it satisfied? Is it not? And so on. Hence, we decided to verify and validate the software by using an approach that we called modular machine development, because actually it is complex to model in hardware-in-the-loop the whole machine, because it is complex to handle all the computational interaction in communication and for all the physical process. So we decided to use an incremental approach, which means that we start to model a certain part of the machine, a standalone, and then all the first layer of those kind of small parts of the machine. Then we test them, we verify and validate them, and then we start to aggregate them all together until we reach a certain level of verification and validation of the software. So this is a schema of our approach. There is actually a model part of the machine on the MATLAB, and then there is a part of which is in charge of writing the data of the sensor directly into the PLC memory, and then reading the data for the actuators of the PLC directly into the model. So, summarizing some results. So, for the flexibility, which means for the three-layer architecture, we developed a set of 11 libraries, which they have more than, I think, we are around 1,000 of software components. And here we have an example in the motion library of two different axis devices, the AX5000 provided by Beckhoff and also the XTS provided by Beckhoff. They are really different. One is a rotary axis and the other one is a linear one. And so basically we can see that actually we had a percentage of reused code about 70%, which means that this percent is defined by the number of methods that we had to overload or change, which means that only the 30% of those methods of those code had to be changed. Additionally, we also obtained 2 different design patterns to model state charts directly into the code. We also obtained a way for generating the testing automatically and run them, and this is a time diagram which is in one of our specification, and here there is the actual result that we obtained from a test. And finally, we have another example of the hardware in the loop. So here we have the real behavior of a module, and we have the simulated one that we obtained during the HIL. So, concluding, we propose a set of methods which try to handle the flexibility through an abstraction architecture, the reactive behavior of the components of this architecture with the state machines, and then by also using object-oriented features to improve the maintainability and reusability of the software. We also created a tool for the automatic generation of the documentation, and also 2 different methods and tools to handle the testing and the verification and validation of the software. So, concluding some of our publication that we have done in international conferences, and I finished, I think. Thank you, everyone.
Thanks for your presentation. Any question? Okay.
Yes, I think that the problem of keeping the same concept in the different phases of the software development is very relevant. And mine is a suggestion. There is an approach called models at runtime, which aims at keeping the same concepts from the model of the software to the runtime execution. Yes, something like this. Yes.
Thank you. Thank you. That's a clever question, actually. And we thought about that, but because actually there was another group inside one of our industrial partner that was dealing with that, but they had an issue. Actually, when you do that and it works, but then when you go to a client and you have to build your machine and you have to edit something in the code because you have to do some tuning and so on, that code is really messy. You wouldn't understand any line of that code. So we wanted to produce something that was easy to do and easy to maintain and easy to edit for the tuning or whatever. So, but
yes, I understand. But the idea is that you don't have to modify the code, but you have to modify the model. But I think that in your case, perhaps are more the need is also to modify the code at the customer side. Yes. Okay. Thank you.